Okay, so hopefully you remember from yesterday that this is what a binomial distribution is. If we want to find the event for a binomial distribution, we take the number of arrangements which we find by its combinations. We take its probability of success and multiply that out, and then its probability of failure and multiply that out. So this is kind of the form we were used to yesterday, and we did different things to find exact. So given an event that you have a 25% chance of happening, and there being 5 trials, if you want exactly 3 wins, take its combination, find this. So this would be about 9%. And then it was a little bit trickier when we had like greater than 3, so you had to do 4 and 5 and add the two things together, and that was a little bit lengthy of a process. But you could still find an answer for this. So moving into today, since that process is lengthy, we kind of want to know the shape and what this thing looks like. So we're going to take that event with the 5 children and having a 25% chance of getting O negative blood. And when we're looking at this, we can find the success rate for none of their children having that. 1, 2, 3, 4, or 5 of their children. And so we can make a chart like we did last time. And again, we can then graph it in a histogram. So this is a table like our expected values that we've had before. This would be our histogram. And if you look at the shape of that histogram, it looks approximately normal. It's a little bit skewed right. And then if you look at its center, we could guess that its center of the thing would be around 1. So let's see if we can find its mean. And if you remember how you find the mean, it's this formula from before. We would take each of these numbers and multiply them together and then add them up. And so when you do that, you find that the mean is 1.25. Then we can do the same thing that we did to find the variance before, which means take each of these events, multiply them together, subtract them from the mean, and then square it. And then after you add all those different things together, you would find that the variance is 0.937, which isn't that useful, so we'll take the square root of this thing. And we'll find that the standard deviation is 0.968. So we could find the mean of this thing and the standard deviation. One interesting thing happens. If you do this every single time, you'll find that these formulas start happening, or these patterns start happening, where the mean is always the number of trials times the percent of success. And if you look over here, we had 5 trials. The percent chance of our success was 25%, so that's exactly what we got when we calculated the long way. So again, it will be your number of trials times your success. Percent success, I guess, is the better way of putting it. And then standard deviation looks a little bit more complicated, but it's still pretty much the same thing. It's number of trials times the percent success, and then you just like this right here would be your percent failure. And then that would be your variance, so when you take its square root, that's the standard deviation. So let's see if we can figure some of this out. Okay, let's say we're giving a distribution, and let's say in this AP Stats class, they did an activity on one of the pages of our textbook, and we assumed that a third of them can't tell whether it's tap water or bottled water. So let's figure out the mean of this distribution. So out of 21 students, the number is 21. The success rate of being able to tell is a third. If we want to find the mean, we just take the number, times it by the percent, and we'd find that that's 7. And we'd expect 1/3 of the students to guess it correct, or about 7. So this is like the most likely number to come up is how we're going to deal with mean. So it's the most likely number. Now we could do the same thing with the standard deviation. And the standard deviation, again, would be the number of trials. And this would be the success rate, which would be 1/3. So that means the failure rate would be the opposite, or 2/3. And when we multiply all that together, we get about, and take its square root, we get about 2.16. And today I want you to round to the hundredths on these things. And this, we would say that it would differ from the average about 2 students. So we wouldn't be that surprised if 5 students got it or 9 students got it. So it differs from the average about that amount. Now the nice part about being able to do this really is to be able to find these things quickly. Because before, we were able to find areas in the curve using z-scores and some normal approximations. So if we have a mean and we have a standard deviation, we can start to find some of these areas under curve. So let's kind of look at these different things. So they're saying we have a success rate of 0.8, and just looking as we increase the number of trials. And as you can see, as we increase the number of trials, this thing looks more and more normal. And the curves, like if you have more than 10 trials, or larger than, well, not larger than 10 trials, but if you're larger than, if the number of trials times your probability is bigger than 10, and the number of trials times the failure rate is bigger than 10, or equal to, this distribution will be approximately normal. And if it's approximately normal, we can just do everything that we did before. So let's say we have this survey, and let's assume it is binary, and we can check that, because if we have 25,000 adults, and they're agreeing or disagreeing whether they like to buying new clothes. So it's a yes or no answer, definitely agree or fail, and suppose 60%. So we have a success rate, which is that 60%. We have a certain number of trials. It can't get more than 25,000. So we can find this thing. And if we want to estimate that 1,520 or more samples agree, well, before doing that would be a nightmare, because we would have had to do, we want x is greater than or equal to 1,520, which that would take forever. We'd have to find 1,520, 1,521. So we don't want to do all of that. So now, since we can approximate its normal, we can find its mean and its standard deviation. So its mean in this case would be my number of trials times my 0.6. So there's my mean. And then we can do the standard deviation, which would be the number of trials times the success rate times the failure rate, which would be that. And then if you have the mean and the standard deviation, you can find a z-score. So we want everything that would be above 520. So 520 minus our mean divided by our standard deviation gives us this thing, so z-score. We can then look that up in the chart. And when we look that up in the chart, we get this number right here. But since we went above and this chart only shows below, if we subtract that from 1, we would get that percent. So it becomes a lot easier to do by throwing it into z-scores. And again, the qualifications for this being normal is the failure rate has to be, the mean has to be bigger than 10, and then the failure thing has to also be bigger than 10, because we need enough trials to make it approximately normal. Okay? We're going to try one more type of problem, and on this type of problem, we're going to use only our calculator for this thing. So I have a Gallup poll, and in the Gallup poll they said that we have a 43% success rate, and we have 15 college students. So the first thing we want to check out before we do anything is let's make sure that this thing is going to be approximately normal. And if we do that, our success rate would be 0.43 times 15, and we would get 6.45. So this would not be approximately normal. So these answers that we get might not be exactly right, but because it isn't approximately normal, but we can still find some of these answers on a calculator and try to at least get close. So here's how you're going to type all this stuff into your calculator. When I pull up my calculator, there's two major commands if you go to distributions. There is, if I scroll all the way down here, there's a PDF and a CDF. The PDF is going to give you exact answers. The CDF gives you everything below. And I'm not quite sure what the P and the C stand for, but I just know the PDF is the exact answers, and the CDF is everything below. So since this is an exact answer for the first one, we're going to use a PDF. And so we're going to go up to Binomial PDF because it's an exact answer. We're going to hit that. And here's how you enter this stuff in. You enter your number of trials. Then you answer your percent success rate. Then you're going to answer how many that you want, and we want 3. And when you put all that in, it will give you your percent. So we know this is, hey, this is about 4%. And so again, this is PDF because it's an exact. Now this is a range. So if we want the range, we want to find 5 and below. Then we want to find 11 and below and subtract the 2. So if you kind of think about like where it would look on these kind of things, if I find 11 and I find 5, and I find the difference of the two things, I would be able to get this region right here. So let's do that. So we're going to do, CDF this time because we want a range or below. So the first one we would want to do would be 15, comma, 0.43, comma, 11 trials. We're going to subtract that from binomial CDF of 15, comma, 0.43, comma, 5 trials. And we would find that that range is about 68%. So again, CDF is going to tell you everything below. It's going to give you a range. PDF will give you the exact answer. For CDF to really work properly, you want this thing to be approximately normal. But if it's not, we can still get an approximate answer. So try the different problems today and see if you can come up with some of the solutions.